Okay, so now let's move on to the problem that requires us to use a one-way repeated measures ANOVA. And the reason we know these are repeated measures ANOVAs is because the independent variable is a within subjects variable. So like if we look at this first question, does BMI is the dependent variable, does BMI change from wave 1 to wave 3? Well, the same people were measured at wave 1 as are also measured at wave 3. And one of the important things to think about when you're running a within subjects analysis is that these variables have to each be entered as a separate variable. So our between subjects variables go down, if that makes sense. So it's different people in each of these rows, but our within subjects variables go across. So when we go out, we've got BMI down at the end because we calculated those variables. We see that we've got data for BMI at wave 1 for subject number 2, and then we also have data at wave 3 for subject number 2. So the within subjects variables have to go across, or I should say down, I guess. There's a separate variable for each within subjects variable, but the between subjects variables just require one column, and then you code people as being male, or this is sorted by sex, so or female later down at the bottom. Okay, so to run a repeated measures analysis of variance, you're going to go to Analyze. You go to the same general linear model where we went for the univariate analyses, but now you can see there's a separate option here for repeated measures. So I'm going to click on repeated measures, and this is interesting because what you have to do, or what you get to do, is to give the within subjects factor a name. So BMI from wave 1 to wave 3, I could call it wave. I think I prefer time. I just give it whatever name I want to, but that's how it'll show up in the results, so it needs to be something that's logical. And then I tell it it has 2 levels because there's wave 1 and wave 3. If there was wave 1, 2, and 3, then it would have 3 levels. Okay, so I add that here, and then I click Define. Now you can see that it set me up to put in a variable to use for my time 1 data and a variable to use for my time 2 data. And again, they're down here at the bottom. So BMI at wave 1 will be level 1 of time, and BMI at wave 3 will be level 2 of this variable called time. Okay. If you ever in your own work need to do a mixed analysis of variance where you have time and some between subjects factor, like does BMI change differently across time as a function of sex, then you would put sex in here and you'd be running what's called a two-way mixed ANOVA, but we didn't get to that in class and we didn't solve those by hand, so I'm just telling you about that as an FYI, but we're not going to do that together. Okay, so then I always want to go to Options, and I'm going to ask for Descriptive Statistics. The post hoc options on repeated measures are not good, okay? So you end up having to do some different steps if you have 3 levels, but again, that's beyond what we're going to do for this class, at least on the SPSS portion. So I'm going to hit Paste here, and then I'm going to go to my syntax window, and I'm going to highlight this, and I'm going to hit Run. And these results are going to look a little bit different than what we've seen thus far. Again, this just lets us know that we clicked in the right things. We're looking at wave 1 and wave 3. Here's the descriptives we asked for. This is a table that you're actually going to ignore. Okay, so you're going to ignore this table. This table you can ignore right now because we only have 2 levels. But if you ever are running this with 3 levels, then this is a test for one of the assumptions that's similar to what we do, like if you want to think of the independent samples t-test, where you're looking to see if you meet one of the assumptions. And so this is testing to see if you meet the assumption of sphericity. It's irrelevant if you only have 2 levels, so we only have wave 1 and wave 3, but if you had 3 or more levels, then you would look here. If this was significant, that would be a bad thing, because it would mean that when you came down here, you wouldn't be able to assume sphericity. In other words, the null hypothesis says that there is sphericity. If you have a p less than 0.05, then you're going to reject the null, and you're going to say you do not have sphericity. And then you would come down here and you would use some of these adjustments to make an appropriate adjustment to degrees of freedom reflective of the fact that you failed to meet the assumption. Okay, again, I know this is more information than you want, but I just telling you about it in case it comes up in your future. Okay, so this is the box where we want to look. we're looking at the tests of within subjects effects. We get to assume sphericity because we only had 2 levels of time. So we're going to be looking at this information. And I already glanced and know that it's significant, so I'm going to make it green, but let me show you where that is. You can see here that it is significant at p less than 0.001. Okay, so that's what you're going to write then into your conclusion statement, which is asking if asking if BMI changes from wave 1 to wave 3. And so what I've done is I've just written in a sentence, and I've gone ahead and incorporated the means and standard deviations, which again I find up here. All right, so here's the descriptive statistics that tells me what the mean at wave 1 was and the mean at wave 2, and so you can see that it increases from wave 1 to wave 3. Wave 3. So that's how I wrote it in here. BMI increases significantly from wave 1, and then I put in the descriptive information, to wave 3. Here's the descriptive information. I put in my F with my degrees of freedom, which came from the source table. 1 and 4602 degrees of freedom equals 3608.24 p less than 0.001. And then actually I'm done with that question. So I will leave this next one to you all so that you can work it on your own and make sure that you're understanding how to do these repeated measures ANOVAs.